Welcome. This is our last week of new materials. Since next week we're going to have our presentations on your projects and so forth. And I want to leave an open option for you to kind of ask some questions as well in one of our final discussion boards. So we want to get into elliptic curves though, because this is actually a really, really important area of what we do in cryptography. So in order to do this, we're going to have to actually start with talking about group what are groups again? Because everything we've done actually up to this point in time has involved groups. There's a reason we've talked about this abstract algebra structure, is it's fundamental to what we do. So a quick reminder, what is a group? A group is a binary structure. So that means it's a set that is closed under an operation we will call star. Now, the truth is, you could call it star, you can call it asterisk. Some texts will even call it a plus symbol. Um, these are not the normal addition, multiplication, and so forth. There's some operation that we define, and they could be the normal addition and multiplication, but they also might simply be just a way to think about it. So it could be things closed under matrix multiplication, under matrix addition, which are different sort of things. There's lots of different options here. There's even some different things called some different groups that we can deal with in terms of like geometrically flipping and turning and so forth. So without getting too technical, I'm going to leave that off. But the idea is here it has to have three properties when we create a group. And we've actually been doing all this with a group for a second. So we've had associative groups, meaning if I take any one of them and multiply by another two, that I can multiply two together and then multiply the third, or essentially do them in some way. So I'd either do the first two or the last two and then multiply the third one in, but they have to still be on the same side. This doesn't mean that you can commute them around. That's commutative property, but it means you can kind of group them. How are you grouping it? It goes off on your own. Existence of an identity. Now we're going to call this identity 1G. It means any element operated on that one combined with that other element with our operation star is just going to give me back that element. It's not going to change the situation. And last but not least, the existence of inverses. This again, remember this notation here is for inverses. It's not a true power, and this is going to become even bigger with what we're going to talk about as we kind of go forward with this. So we're going to have all of these things that we're going to have to check on, and we're going to make sure that we understand, because elliptic curves actually have this. And we've been doing this already with everything else that we've already been talking about. Namely, we've been using some cyclic groups. Now, a cyclic group is a group that's generated by one element. In other words, there's some element that a to a power, because if we use star as multiplication, then this is that power. So when we did Z mod P or even Z mod N, that was the group generated by, well, take one and add it to itself several times and you get Z mod N. So we can generate everything by doing this, and that's going to generate it all the way. So we need one element, at least one element that generates it. It could be multiple elements, but there's at least one element that does this. Now, going back again, so I want to hit this very clearly. Z mod N that we dealt with, remember, one of the things we've already dealt with is we used, because you're dealing with integers, they had this associative property. We're going to go away from integers today. We're going to do this different kind of structure. It's integers and modular arithmetic are still involved, but now we get crazy. We're going to talk about what are the identities in our situation? What is the inverse of our situation? Because those are going to be two things that are going to be kind of crazy and really, really hard to understand. All right. So let's get into those. So let's talk about elliptic curve and what on earth is it? So to understand our motivation, why do we even care about elliptic curve? Well, because we've already done some public encryption. We know RSA is crazy cool. We've done some other things with digital signatures, the DSA, and so forth. Well, the truth is, if you ever compare this is the security level in terms of bits, where AES, if it takes 80 bits, because we know the symmetric system actually takes less to encrypt, because it's already symmetric. That's actually one of the beautiful parts many of you have not noticed, is that symmetric systems actually take less information to, because we just have to keep it secret. That's the only difference. Whereas when we put stuff out in public, it takes a lot more. So if you do 80-bit encryption, you actually need 1,000 bits of RSA or even DSA together. This is from a textbook that I have. These numbers keep changing. There's slight variations, but this is pretty darn close. Similarly, if I just went down on, if I was just an elliptic curve, though, notice an elliptic curve only needs like 160, yeah, up to 223, but only double the bits of AES. Same thing if it was 112, we have 224, 128, 256. You start seeing this trend here that the relationship is almost eccentric, is only double. And that is a beautiful thing because that's far less than the 10 times as many bits that I need in order to do RSA or DSA. So if we can do our encryption with much fewer bits, that's great. And I know all of you are like, who cares about memory? We don't need memory. Well, remember, memory requires computation. The less computation we have to do, the better, the smoother it is. So what is an elliptic curve? Well, the technical definition of elliptic curve is this. It's the set of equations to the Weierstrass equation, y squared equals x cubed plus ax plus b, with an extra point O, where the constants a, b are satisfy the equation 4a cubed plus 27b squared is not zero. I'll talk about this in a second, but let's go back to this as well as to kind of illustrate something. I'm just going to kind of switch screens real quick. Let me hit something. We're going to go over here. I'm going to pull up a graph real quick. And I want to show you that long ago in your high school days, you looked at the equation y squared plus x squared equals 1. And you got this wonderful thing. And even if I change this number from 1 to, let's say, 6, we get bigger. If I make it r, it doesn't really exist. If I go 10, it makes it bigger. Remember, these are all the sets of values on here. Now remember, this is a point. It's the collection of x's and y's together that satisfy this equation. If we start messing around with this and start giving, let's say, coefficients in front of those, so let's come back up and let's change this to be 2x squared plus 3y squared. We get this. It's not hard, easy to see that that is actually an oval, but I'll make this 8 and I'll make it even better. You can really see this. Still, we have this beautiful oval shape. It's kind of cool. What if I make this subtraction instead of addition? Well, we get this, which is hyperbolism. We can kind of still, these are structures that we can build on, we can utilize. And these hyperbolic kind of structures are really cool. And so we start adding more things, and then we get into something that looks like, I'll just pull it up real quick, y squared equals x cubed. I'm just going to do that. And I get this kind of interesting little cusp thing going on here. If I just change that slightly to go minus 6x plus 2, we have this where I now have an O, and we have this. And again, I can modify this ever so slightly to have this be 10 now. And now we got a cool shape. This is the shape of an elliptic curve. Now, elliptic curves are these beautiful things. Because as you look at it, there's a couple things you can probably start to notice very quickly. First, it's symmetric across the x-axis. So that means it's the same above and below. That's a great and wonderful idea that we have going on here. And so we're going to leverage that to kind of understand a couple things. So jumping back to my other screen, if we are looking for anything that's of this form right here, y squared equals x cubed plus ax plus b. Now, the reason for this constraint, remember I did that first example and it had that little cusp? Then I had another one where it had an O. The ultimate goal is if we have this property here satisfied, that at minimum the cusp is gone and most of those O's kind of go away, and it really makes it a more general option that lets us do a lot more. So we really kind of care about it. So we're going to talk about this is a set of points. So this, if you pick an A and B, there's going to be a whole bunch of points on here. And then we're going to throw an extra point here. Now, what is this point? I'm going to tell you right now, this is infinity. Not the actual infinity, but it's a point that allows me to go to infinity. And so it's a general terminology because there is actually, by the way, when we deal with very large things in abstract algebra, we will sometimes include the element infinity, and it has to be defined specific ways, implying it's infinitely large and things like that and so forth. So we can still do and employ it in the normal real numbers. It doesn't exist, but we're not in the real numbers. The truth is we're not going to do this. I'm going to explain the geometry of this in here, and then I'll go back and I'll show you what it looks like in another place. So we have this. So let's go back to our just image real quick and look at this. So the problem here is that we've been dealing with groups this whole time. We've been building up and creating an object. And up to this point in time, we've dealt with integers the whole time. But what are the things on the curve? Like if I pick a point right here, the problem is my point is two values. It's a point. So no longer am I just talking about integers. I'm now talking about points. And that makes a bunch of my operations that much harder. So I'm going to get to why we have the identity, what it is, and so forth. But let me go ahead and make this grid first off disappear. Settings, grid, get rid of my grid. All right, so what I'm going to do is I'm going to put a second point on here. I'm just going to put it down right here. Now my question is, how do I add these together? Because that's our operation that we're actually going to work on. We're going to add them. Now, I'm going to show you the formula, and this is the formula your book just throws right at you. It doesn't ever really explain. It's kind of like, ta-da! So it gives you this really big formula. And it's like P and Q are 2 points where they're not zero, and we'll talk about what that means. Then we get the following formula. Now, where does all this come from? How did they figure this out? The truth is they came up with that because of looking at the graph. So I'm gonna explain this geometrically, and then we're gonna talk about what we're gonna do. So how do we add points? Well, right here, even if I took this point and I shifted ever so slightly, these points I can't just add together like vectors. I can't just literally add the numbers, the x's together and the y's together, because I want another point that's on the curve. How do I do that? Well, I go and I make a line. Now, if I make a line that goes through these 2 points right here, you'll notice that it intersects in a point all the way down here. And then all we do is we then follow that point. I'm actually going to cheat a little bit. Grab this. I'm going to swing this down like so. Grab that point. I didn't want to go way off the screen. But even still, I got 2 points. All I do is draw a line through the 2 points, and it has to connect to this point. Now I take this point and I make another line. But this line is going to be a completely vertical line. So I'm going to come all the way up, and then I'm going to put a point right there. And this new point D is actually A plus B. So this point D, let's change its color, make it red, is actually sum of this green point plus this green point. I hope no one's colorblind. If you are, I apologize. But A and B, when I add them together, I actually get D. That is how we can actually do this operation to actually get it. Now, to explain the closure, here's why we do this operation. And then I'll explain the identity that's mixed in with it. One, it guarantees me that if I add any 2 points, that it gets me back to the same value. It gets me to another value on the curve. Because take any 2 points on the curve, put a line between them, and you're going to bounce and hit a third point in the curve guaranteed. That is the beautiful part about it, because we have closure on it. Next question is, do we have associative? Yeah, it's hard. I don't want to go too deep on this. I could try to get into this. That's under explaining at the associative property of this thing is really more of a, it's really of an abstract algebra concept. So it's not something I'm going to go into too much right now, but just trust me that it's there. But I will talk about the inverse and the identity. So we just did this and got all these points. All right, so let's just make everything go away. Let's make B, this line F, C, D, and G all go away. So let's come back to our point A. I'm going to slide it back up here. Another question that I do need to ask in this process is what happens if A goes through itself? So remember, we had B that was down here, and we had the line that went through them. Well, what's going to happen if I grab B and I just start moving it closer and closer and closer? Well, from your calculus days, you should remember that that makes the line, if A and B are the same point, it actually is the tangent line. We did this in calculus, which you did a while back. This is why calculus, and still notice it still hits somewhere over here on the curve, and then I can reflect that down and get my other point. So we can add even something to itself. But the question comes, what's the identity? Where's the second point that I would get? Well, that's where we had the notation. Let me go back to it. Add this O notation. This is going to be infinity. So where is infinity if we're looking on our graph? Infinity's up here, way up high. So if I take my second point B, and I'm actually going to get rid of that. I'm going to give it a new point. I'm going to make it way up here, and I'm going to make a line between this and this. We quickly see that this actually, it goes off to infinity above. I know I didn't put E all the way infinity, but you get the idea. It's at the very top of the page. It's not on the curve. Well, this actually does something very, very interesting. If I was to add the points doing what we did before, so I'm going to take this point and I'm adding it to this point. It takes me here, but then we reflect back up, which sends me right back to A. So from this way, having any point A plus the big O notation takes me right back to A. Therefore, it is the identity. It is the thing that guaranteed will get me back to the identity. That is perfect. So we have an identity for everything. And no matter where A is, the identity is always this infinite element that we got going on here. Now, what about the other part of it? What's the inverse? Well, it turns out the inverse is actually this point right here. Because if you look at it, that inverse F, A plus F, if I add them together, they don't actually hit anything else on the curve, but they shoot off into infinity. And so it turns out that the inverse, written as negative P, let me write that down for you. This right here, if this is the point, we'll call it P, then this point down here is negative P, because P plus, I'm not going to always do it, but I'll put this symbol, negative P is equal to that curly QO. That's the infinity. So that is where we have this. This is a negative value. Now that means that for any P, which is X, Y on my graph, negative P equals X what? Negative Y, because it's just a reflection. However, you have to be very, very careful because this right here means two different things. So this negative does not actually mean subtraction. It means the inverse, the additive inverse. Whereas this does mean subtraction because I took the negative, the y, and I made it negative. So if it was negative, it now became positive and vice versa. So this is kind of a fair warning right now. Pay attention. This is a common mistake that students make. And it turns out this is actually pretty nice because if you know P, finding its inverse is pretty quick and easy. And so we really, really like that fact about how we can attack it that way. So let's come back here and let's talk for a brief second more about the elliptic curve. So I've kind of tried to water that down. To be honest, there's a lot of videos. You can go Google and look at other stuff. But the idea is that we are going to be adding points on a curve. The problem is I just explained this geometrically on a graph. But we can't do this on a graph. We want integers. So we're going to add a modular arithmetic into it. And so when we come here and we use this formula, we're going to get that. Now, let me explain this formula real quickly for you. I'm just going to point out something real quick, a couple things. First, let's talk about the S values. What does this first S value look like? Hopefully you're saying, at least in your head, it looks like it's a slope formula. And it is because if remember, if you have P and Q and they're not the same, then we're going to have a slope. So we're doing the line between them, and that's going to be with the S. So if I have this, and I know my drawing is horrible, I'm drawing my straight line. Sorry. This works a lot better on chalkboard. But the slope of this line, the slope of that line is going to be y2 from down here. This is the point x2, y2. This is the point x1, y1. That's going to be y2 minus y1 over x2 minus x1. Because that's the formula of a slope. Where do we get it for this one? Well, remember our equation of our line that we're dealing with is this. If our curve is y squared equals x cubed minus ax plus b. What happens if I take the derivative of that with respect to x? Well, that's going to give me, going back to your implicit differentiation, this is equal to 3x squared minus a. Oh, sorry, this is plus a and this is plus a. Do you see a trend here about those two values, about where we're going with this thing? Because we're taking the derivative, now all I have to do is divide by this, and I get my magic formula right there. So the truth is, this formula, this S is for slope. As for the rest of that, you can kind of work through it. It should make sense once you stop and think about actually where are we building this from, that we're actually trying to solve the equation. S, we have, so if I have a line that goes through any point, it'd be S, and then I have to put in the two different values. I have a point we're trying to work between. And that is actually going to be the idea behind how we get here. So y would equal s times the x1, the difference in, yeah, x minus x1 plus, sorry, yeah, plus y1. And if you look at this, this looks a lot like this thing right here. And that's actually the general idea that we are trying to solve on. but we then also have to plug that into my equation, which is y squared equals x cubed plus 3, not 3, ax. I don't know why I keep jumping ahead. Ax plus b. And if you take this and plug that in over here, I now have a cubic and I need to find solutions, namely 3 separate solutions to it. All right, so that's the idea behind how all this works. If any of you want me to explain this a lot more, I'd be happy to. This is the beautiful part. This is not crazy. However, you are going to use this formula and this a lot. And the thing is, this is going to get a little bit, there are ways to still program it up. You can write your own thing where you can have a function and you put in your x and y and it does the calculations depending on the different things. You have to put in 2 points, x, my p and my q, and you'll have to calculate then based on those values. All right. Let's continue on though. We just talked about how the addition works. So let's actually do an example. So this is x cubed plus 2x plus 2. And now I'm going to change it to mod 17. Now, the truth is these equations still hold, but the geometry of how it works doesn't make sense because if we're in mod 17, then we don't have this structure right here going on anymore. Instead, if we do all of this, all we're left with is kind of trying to figure out, how do I make all this work? So let's just kind of wrap it up by walking you through the example. So let's do our example, which again is y squared equals x cubed. Oh, 2x plus 3. Did I get that one right? Plus 2x plus 2. My bad. I knew that didn't look quite right. Okay, so this is my equation. I'm going to go ahead and get rid of everything else. This is the equation upon which we're going to do this. And we're going to do this mod 17. So it's not even going to look entirely like this. This is just to give you an idea about what we're kind of playing with. Now let's go back and go through this process. So if I want to find this, be careful because too many people see this and they think, I'm just going to warn you, they would be like, okay, well, that's going to be 5, 1 plus 5, 1. Well, that must be 10, 2. And they just do the straight vector addition. It's not actually equal to that. And I'm going to show you it's clearly not equal to that. But that's the problem is be careful. This is not vector addition. This addition is defined very specifically for elliptic curves to make it hold as a group and to make it not only a group, but it's actually technically a cyclic group because we have to have one element that generates everything. Namely, I can use P to generate everything. And I'll show you that later. But let's continue on. If I have P is F is 5, 1, the first thing we need to do is figure out my S. Now, because P is equal to Q, because we're doubling it, S is equal to this thing, which remember is the partial derivatives of our general formula. So what is A? What is X1 and Y1? Well, A is 5. Sorry, A is 2. It's from up here. X1 is 5 and Y1 is 5. Y1's 1. Yeah, wow, I can't even talk right tonight. I'm pointing right at it and I can't even say it. So if we multiply this out, we get 77. Now here's the problem. We're going to take mod 17. So dividing by 2 doesn't really make sense. If you had just simply written this out as this is equal to 77 over 2, and then been like, well, what is that? And come with something like, that's 38.5. That's not going to work in this situation because we don't have any decimals and we don't have other things. So what we actually need to do, instead of dividing by 2, we are going to multiply by 2 inverse. And that exists mod 17. So now all I have to do is find what is 77 mod 17, what is 2 inverse mod 17, which are going to be 9 and 9. Actually, ironically, they're both 9. Then when I multiply those two together, I get 81. Take that mod 17, you get 13. So we had to work through this problem. It was a little bit more complicated. And guess what? We're not even done. We just had to find S. So the first thing we found is S. Now we take that S and we can plug that into our x3 formula, which states that x3 is equal to s squared minus x1 minus x2. Remember, x1 and x2 are the same because the point is the same. So this is going to be 13 squared minus 5, or 169 minus 10, which is 159, which is 6. So just like that, we have our s and we have our x. And now your y value, as a reminder, was s times x1 minus 3 minus y1. Multiply these things out, we get 13 times 5 minus 1, which is equal to negative 14, which is equal to 3. And that is indeed our 0.63. But how could I know for certain? Just real quickly, this is a good rule just to have in general. How could I know and guarantee my answer is right? If you go up here and plug in 6 and 3 into this thing, we would get 3 squared. And then we have to figure on the other side 6 cubed plus 2 times 6 plus 2 mod 17. So this is going to be 9. This 6 cubed is 36, which happens to be 2. So this is 2 times 6. It's 2 times 6 plus 2 mod 17. So that's 24. So it's 26 mod 17, which happens to equal 9. And just like that, we've shown it's true. All right, hope that helps you understand elliptic curves and get going at them. Get started with the examples and let me know what questions you have.